So, in fact, to do this, I will start from the beginning. I will try to answer 3 questions. The first question, who are us in this vast universe? Who are the human beings in this vast universe? The second is how much science we know and what are the problems with science today. And the third part is what is the future of science? How we can correct our understanding of the universe. So let us take the human being in space and time. Let's start about the human being in space. Who are we in space in this vast universe? If we look at our galaxy, we have about 100 billion stars in our galaxy. There are 10 trillion galaxies in the universe, in the visible universe. So that makes the number of stars in the visible universe is about 10 to the 24th star. That means million, billion stars in the universe. I will assume that each 10 of these stars have one planet. So in fact, I have 10 to the 23 planets in the universe. The question is, how many of these planets are Earth-like? يعني يشبه كوكب الأرض. Now I have to go to the data of Kepler. Data of Kepler says that 7.6 of stars discovered so far, where there are planets, are G-type. G-type star is a star like our sun. Our sun is a G star. Now, so 7.6 of the planets, I will assume statistically, 7.6 of the planets of the universe are around G stars. Now, not only this, 1/4 of planets around these G stars are in the habitable zone. They are rocky planets in the habitable zone. So a rocky planet in the habitable zone is an Earth-like planet. So let us calculate the Earth-like planet. I have the total number of planets, 10 to the 23. I multiply it by 7.6 times 0.25, which is 1/4 of that. So 2% of the planets are Earth-like, and I come with this figure, 1.9, 10 to the 22 planets, Earth-like planets in the universe. So you can imagine when Carl Sagan says that Earth is a pale blue dot in the universe. Pale blue dot in the universe. حباء زرقاء ثابتة زرقاء في هذا الفوق. So in fact, if I look for a human being, we are on a planet which is, there are so many planets like Earth in this universe. I'm not talking about life, I'm talking about just planets like Earth. Okay, now let us see in time. This is in space. As a human being in time, who are we? Now in time, we know that the age of the universe is 13.8 billion years. The age of the solar system is 4.6 billion years. This is what we know about the solar system. Now you have the first human being, I can say, or human-like creature here on Earth is 1.92 million years old. So you can imagine how I'm coming from 4.6 up to 2 million. Now the Homo sapien is 300,000 years. The oldest civilization we know is about 50 to 65,000 years old. The civilization we know modern time, the Egyptian civilization, world marketing, Indian, Chinese, etc. All they are 10,000 years old. Now, our technology, how old is our technology? The first industrial revolution is only 270 years, which is very, very short in this 13.8 billion years old. Now, the modern science is only 120 years old. Now, the fourth industrial revolution is 52 years old. And all what we know about technology and science is about 100 years old. So I can imagine 1 century only, the human being during 1 century only. So all what we know now, in fact, is the product of the last century. Now I will go how we understand the natural phenomena. Of course, at the beginning, our knowledge about the universe is almost zero, because we don't have a model of the universe. All what we say that we have some sort of gods, that we have a god for wind, a god for everything. So anything is explained in terms of gods. In fact, with this, we cannot have any information about the universe. Now, the knowledge increases when we started making observation and measurement. And especially during this period of time. In fact, we use the astronaut, etc., to measure the position of stars, etc. So we have a little bit accumulation of knowledge. Now, of course, we go from this to the principle of experimentation. Experimentations add a lot to our knowledge. But the breakthrough was done here. This is the breakthrough in science. Why? In 1687, Newton discovered, or whatever term you use, discover, whatever, the laws of nature. The laws of nature, for the first time, we've been able to express laws of nature in terms of mathematics. And I mean in terms of mathematics, that means you have a predictive tool. You can predict what will happen next. So the two important laws. First, the laws of motion. Second, the law of universal gravitation. This is the beginning of new science. What next? I call this the most important experiment in the history of science. Why? This is a black body radiation. If I take a piece of iron and I heat it, iron starts becoming red, yellow, etc. In fact, as I heat the iron, it will emit more and more radiation. And these radiation emitted by a piece of iron in all wavelengths, from infrared to X-rays, if you like. This spectrum, or the intensity of emission in terms of wavelength, is called black body radiation. Scientists been unable to explain why we are obtaining this curve of black body radiation. All the theoretical work at the beginning before 1900 produced this yellow line. I call it ultraviolet catastrophe. Now with this, there is no progress. I am unable. There is something missing, in our understanding of physics. Why we are not obtaining the black body radiation spectrum? Then suddenly, in 1900, the answer was given by Planck. What did Planck assume? Very simple assumption. that atoms absorb and emit radiation not continuously but in bundles. In bundles of energy. Now, bundles of energy, and he produced exactly the black body radiation. Stop. That is not the explanation Einstein says. No. This is wrong. The atoms emit and absorb radiation not because their intrinsic property, because radiation itself consists of bundles of energy that he called photons. So even they reach the same explanation of black radiation, but their mind and the explanation is different. With the same mathematics, Einstein used the same mathematics, and he produced the same case, but assuming that light consists of photons. Of course, later on, there was dispute between Planck and Einstein regarding this point, but Einstein won because of the other effects. For example, the photoelectric effect, prove that the existence of photon. There's the Compton effect, which also proves the existence of photon. So you see how scientists are thinking to explain the same result they have coming from two different directions. Now, let us see what we have. Now, this experiment, I talk about black body radiation, this is in fact the birth of the quantum mechanics. The birth of the quantum mechanics is the black body radiation, and we know that radiation consists of discrete bundles of energy. And then, of course, we use the idea of quantization to explain the motion of electrons around atoms, of many phenomena in the micro world. Now, the other theory we have is the general relativity. Now, is there a way to explain the whole universe in one theory instead of two separate theories? The question was tackled or treated by Einstein. He said, okay, we have two forces in nature. The first force is gravity, the second force is electromagnetism or electromagnetic radiation or electromagnetic force. So how we can write down a theory that combines gravitation and electromagnetism? He tried, but useless. And I will explain why he didn't find a theory of unification between these two forces. Suddenly, in 1925, Kaluza and Klein, or Kaluza basically is, I think, Polish scientist, produced a theory that combines gravitation and electromagnetism. They give the paper to Einstein for reviewing. Einstein put the paper in his pocket for 2 years. Why? The mathematics is great, everything is great, but there is one problem. The problem is the Kaluza-Klein theory, in fact, is in 5 dimensions. And Einstein said 5 dimensions? What's 5 dimensions? We know only 4 dimensions. 3 plus 1. 5 dimensions is impossible. That is why he put in his pocket. Then how to take the publication from Einstein's pocket? Klein did it. How he did it? How he did it? He said, okay, this fifth dimension, we can make it small up to the Planck scale, 10 to the minus 33, something. This process in mathematics is called compactification. Compactification. بالعربي الالتزاز. Now, compactification. So, if I compactify the fifth dimension, that is why we don't see it. So, Einstein, with this idea, accepted the paper and was published. Initially, yeah. The problem is solved.
هو رفضها.
أي بعدين قبلها. لأن since you get rid of the fifth dimension by compactifying it.
طب يا دكتور شوقي ليه ما تقبلتش كنظريه موحده واستريحنا من الصباح دي
في strong force وفي weak force.
I will go to some problems in quantum mechanics. Of course, you have uncertainty principle. You have the decoherence or collapse of the wave function. You have the particle. You have the particle wave duality. All these are problems. You have the Einstein-Rosen paradox, and this is something that I will talk about, and it's very important. All these things are unexplainable. So there are two ways to, or I just put here two interpretation of quantum mechanics. In fact, there are many. This is the probability theory and many word interpretation of quantum mechanics. I will not go through this. This is very complicated. Each one needs one complete lecture. But these are the problems of quantum mechanics. These are the problems of quantum mechanics. And the question is, do we have a solution? Can we perceive a solution in the future to solve these problems? The other point, which is very important in the history of science, is how Einstein and his colleagues, other scientists, are thinking. Einstein, one day, somebody told him, "Oh, your theory predicts a Big Bang." The guy who told him this is discipline, Lemaitre. He said, "Oh, there's a beginning." Yes, there's a beginning for the universe. Einstein was not aware of this. Then somebody else told him, "Oh, your theory produced a universe that is expanding." He said, "Oh, expanding universe? Stars are there always the same. This is impossible." In 1928, Hubble told him, "No, the universe is expanding. We observe a redshift of galaxies, of far away galaxies. A redshift is produced by something that is going away from
seed.
Okay? I will come to it. I will.
ده ممتاز بس كده.
الزميل يعني حط نقطة ممتازة. يقول إن فريدمان he is the first one who explained or he find out that the universe is expanding. In fact, yes, Lemaitre from the Big Bang, and the expansion of the universe, in fact, was found by Friedman. Friedman, by solving the Einstein general relativity theory, he find the following. He find a kind of cyclic universe. Universe will go to maximum expansion and then shrink, etc. Cycles. This is the theory of Friedman. Of course, this was only theory, but practically, the universe is expanding. This is very, very strange idea. Einstein, to correct this problem that the universe should not be expanding, he added what he called the cosmological constant. cosmological constant keeps the universe as it is. We will come back to. Then he discovered no. They told him the universe is really expanding. Huh? He removed the cosmological constant from the equation. You see how scientists are thinking. I'm just giving you an idea how they are thinking. The same with Fred Hoyle. Fred Hoyle said no, the universe is not expanding, and he put the theory of what we call it the Common structure, and there is creation of matter, etc. Of course, one of the problems also is the compactification. So, in fact, when we look at science, there are problems. Problems not only with science, with how scientists are making the interpretation of their results. Now let's have a look at modern physics. We have, of course, the quantum theory started in 1900 until 1926. We have the whole framework of 1926, in fact, the Schrödinger equation. So by 1926, we know everything about quantum mechanics, the general relativity in 1916, and we have, of course, the standard model of particle physics. This is a long story. الدكتور شعبان طبعا من المتخصصين في هذا الموضوع. This is a long story, and we have. I'm showing here all the subparticles we know. They are in two groups, as you can see, fermions and bosons, and we have fermions, and we have also leptons. Leptons are fermions, quarks are fermions, and bosons. Depends it is upon the spin. The left-hand side fermions, they have fractional spin, and bosons, they have integer spin. So in fact, scientists, they have all this to answer. To put a theory that combines electromagnetic force, gravitational force, strong nuclear force, and weak nuclear force. And as you can imagine, with only two forces, it was very difficult to produce a theory which is Caruso's line. Now we have four forces. Can we make a theory combining these four forces? The answer was the following. So now we have to create a theory of quantum gravity. A theory for quantum gravity that combines, of course, the general theory of relativity, quantum mechanics, and we have to put all these forces we know in one frame to produce one theory. However, if we do this, we get a theory which is not not real nor realizable. If I say it right. Okay. What we mean by not real nor realizable? It means that if we produce this theory, we get a lot of infinities. When we apply mathematics to this theory, we get a lot of infinities, and with infinities you cannot work. That's the end. So we have to remove these infinities. Now, how we remove these infinities? There is the canonical approach. And canonical approach is non-perfect. That means in my Hamiltonian, I don't have to put so many terms that I don't know if somebody knows the perturbation theory. I add terms smaller and smaller and smaller to get the answer. The other one is the operator approach. Of course, the first one requires a solution of what we call Wheeler-Dewitt equation. This is the most difficult equation in science and technology. This equation consists of a Hamiltonian operated on a wave function, and this wave function we call the wave function of the universe. Now, this wave function of the universe contains all information we know about the universe. According to my knowledge, nobody can or will, according to what we know in science today, to solve this problem. But Dr. Ammar told me that they solved it. I don't. There is approximate solution. There is no exact solution, and I will show why there is no exact solution for this problem. The other approach is operator approach, perturbative. The problem with this perturbative approach is that we have self-interaction of a graviton with itself. So I have a graviton interact with itself, produce another graviton, and this new graviton will interact with itself and produce another graviton. So you have a long chain of gravitons without origin. So in fact, these are the two approaches to find a solution to our problems in quantum mechanics and general relativity. Now, let us see the breakthrough in chemical approach. The breakthrough in chemical approach, I will not make a discussion. I don't know why I put it in Arabic. This is a long story. Started with Ashketar, and he produced what we call Wilson rings, etc. But at the end, he found an approximate solution to do it equation. And with this, they produced the paradigm. They produced loop quantum mechanics. Now I have to remind you for this particular theory. This theory is not a theory that combines all the forces of nature. It is not a theory of combining the forces of nature. And one important point, it cannot produce general relativity. We cannot produce general relativity, and we cannot produce standard model from this theory. Standard model, I mean by standard model, all the particles and their interaction that we know in the universe. So in fact, this theory was incapable of doing this, but it has a prediction. Now this theory predicts that space-time consists of tiny parts. And so if you have space-time consists of tiny parts, we are expecting that if we have a wave passing through space, so if it is small enough, it will interact with these small sections of space-time. And therefore, their velocity or their speed will be reduced. So in fact, I will have, if I compare the speed of ultraviolet wave with a radio wave in space, I will find a difference in their speed. In fact, this was not discovered. Now the other approach, breakthrough in operator approach. And this is very important. In fact, this is the part where I'm concentrating on during this lecture. Now, this theory predicts many things. It could be reduced to general relativity. So general relativity is a part of this theory. Second, it predicts all particles and their interaction in nature according to the standard model. Third, it unifies all forces in nature. So this is a theory of everything. But it has one problem. I don't know if it is a problem. It is the problem of theory or a problem of our mind. The problem is that this theory, in fact, there are 4 versions of this theory. 4 versions of this theory. So how you can have four theories describing the same universe? In 1995, a colleague of Dr. Shaban named Witten named Witten, he gathered all these theories in one theory, using a notion we call it duality. So with duality, he was able to show that all these theories, the 4 theories, are one theory. He called it M theory, and M for mother or whatever you call it. We call it mother theory. That was around 1995. Since 1995 until now, there is no breakthrough in theoretical physics, and we are flat. For 27 years, flat. Nothing new. Why? I will explain why in a minute. Now, as I said, what is wrong with this theory? What is wrong with this theory is that it talks about 11 dimension. 11 dimension. I mean the M theory. 11 dimension. Okay, we know 4. Where are the 7? Compactified. لا يذكر compactified. Compactified.
هي 5 كانت موجودة.
احداث البعد 11 بعد.
Okay. So in fact, let us see this problem of compactification. What is compactification? And I think if we solve the problem of compactification, if we understand the problem of compactification, we are going to understand one day the quantum mechanics and the universe around us. When you compactify these extra dimensions, you find a kind of objects, we call them Calabi-Yau objects. Calabi-Yau objects are geometrical objects produced by this compactification. They are very complicated geometrical figures. But the friend of Shaban, Witten, discovered something very interesting. He discovered, for example, if you have 3 holes in this Calabi-Yau manifold, these 3 holes, he give an interpretation that these correspond to 3 generations of leptons, which are electron, muon, tau. So what is meant by this is that embedded in these diagrams, I have the laws of physics. So in fact, the Calabi-Yau geometries are the projection of our laws of physics on the very small scale. If I project all the laws of physics I know on very small scale, I get these objects. And no, it's black scale. Black scale. So in fact, what is wrong? Is it something wrong with our mind or with nature? Look here, I am giving always this example. This is a 2-dimensional entity. Now this dimensional entity wants to go from up to down. How we proceed? go this way, and then come here. And somebody is looking at this, he is amazed. Somebody in 3 dimension looking at this guy going this way, and you said, oh, you can pass from here to here directly. If you know how to use 3 dimension, you can just pass from up to down. You don't have to go all this way. I use always this idea to explain the idea of higher dimensions. Now let us look very quick look our knowledge. We have 1687, of course, Newton's laws, and then our knowledge increases when we discover Maxwell's equation, and then increase with the quantum mechanics, etc. And then we reach into the M theory, and at the M theory, since 1995, we are flat, nothing new. Nothing new. Why? Look what. This is our brain. The limit of our brain is what we can imagine is the Calabio. These spaces. The space up to here. Out of this space, we cannot imagine it. Around this space, we cannot imagine it. So in fact, to understand quantum mechanics, or to know more physics, we have to find a gate here. A gate here, we remove these two and go to this space. Can we? Here we are under the domain of philosophy. Something that we don't see with our senses, like the higher dimension. What we do, we just compactify it to 0. This is a big problem. This is a problem with our mind. If I don't perceive something, I reduce it to 0. The reality will not accept this. Reality is beyond our senses. Reality is beyond our senses. So in fact, reality says that there are other dimensions in the universe. The other dimensions, I don't perceive them. If I don't perceive them, I don't say they don't exist. The same as the example I gave just for two-dimensional figure, two-dimensional entity, he doesn't know that there is a third dimension and he cannot perceive it. That doesn't mean that this third dimension is not there. So in fact, these dimensions that we don't see doesn't mean they don't exist. That means our mind cannot perceive these dimensions. If one day we can perceive these dimensions, everything will be solved. I will give you an example. Today we've been talking about, today or yesterday we've been talking about double slit experiment. Double slit experiment, I go back to understand the double slit experiment. I have to understand what is a particle. The particle we know is a three-dimensional entity or four-dimensional entity. No, according to M theory and superstring theory, a particle is a multi-dimensional entity. An electron or a positron or whatever proton is an 11-dimensional object. We see the projection of these dimensions on our mind that we perceive. We perceive from the particle, we are not saying the particles. We are seeing the projection of particle of our reception on a human mind. That is why our notion of particle is not correct. We are looking at particles as if they are three-dimensional. They are not three-dimensional. And that is why in quantum mechanics it is very difficult to make a good interpretation of quantum mechanics without knowing what is a particle. For me, a particle has a wave function, and this wave function is multi-dimensional. It has 11 dimensions. Now, a wave function with 11 dimensions, I am treating all quantum mechanics according to my observation as if the particle consists of just 3 dimensions. No. There are hidden dimensions that I don't see. Doesn't mean that they don't exist. Now, I will go back to one important point. Go back to EPR paradox by Einstein, Podolsky, and Rosen. Now, EPR paradox, you know, the action at a distance. And it comes to the problem of entanglement. Entanglement, we know if I take a photon of spin up, electron of spin up and electron of spin down, put them together, entangle together, and then I separate them, one at the end of the universe and the other at the other end of the universe. If I change the state of that photon, the state of the other photon will change instantly, not speed of light. Instantly. This is what we call entanglement. Now, why entanglement? How we explain entanglement in modern science? Modern science, we say, oh yes, there is something called unlocality. If you go back into internet and check for unlocality, you will get nothing. Explain to you with words what is unlocality, but I believe this is not the right explanation. Unlocality, in fact, is higher dimension. These photons, they are separated far away in my universe. In fact, they are connected together in higher dimension. These two photons that I see separated, in fact, they are connected in higher dimension. Therefore, there is something I don't know, because I don't know the physics of higher dimension, that brings these two photons together. So in future, what will be the course of science? The course of science is discover what are these higher dimensions, how we can use them. If we don't discover these higher dimensions and how we use them, the curve will stay flat. Until 1995, we don't have any progress for the last 27 years in vertical. There is no breakthrough. So at the end, I will give you my conclusion in a simple story. In fact, I will say it in Arabic.
معتذرين نفسنا ودكتور الأجنبية مش موجودة أصلا. موجودة؟ ما كانتش بقى.
Okay. This time I will talk about it. In fact, this story I read when I was a PhD student. This story was written by André Gide. André Gide is Nobel Prize winner. He won Nobel Prize in literature in 1947. And he wrote this story. This story is between a pastor, we call it pastor, and a blind girl called Gertrude. And let us look at this conversation between Gertrude and the pastor. Gertrude, أنا أستمع إلى تغريدة الطيور وينتابني الشعور أنني أفهم ما تقول، ولكن لماذا لا تغرد الحيوانات؟ الطيور الوحدة هي التي تغرد. جرترود، وهل هي المخلوقات الوحيدة التي تطير؟ القس كلا، هناك أيضا فراشات التي تطير. جرترود، وهل تغني فراشات؟ القس كلا، الفراشات لا تغني، لكن لها طريقة أخرى للتعبير عن نفسها من خلال الألوان على أجنحتها. جثث الألوان عمياء ما تشوف، الألوان وات كلرز.
هو ده مش عارفين نحس
This is the same what happened with us. Dimension, higher dimensions. What are higher dimensions? I cannot perceive higher dimension because my mind is not really fitted for that. The same. For Gertrude, she cannot imagine what is color. A blind person cannot imagine what is color, whatever you can. Because his mind is not trained to perceive colors. That is that is why I am saying that at here something that we don't perceive does not mean it doesn't exist. And this is the problem of science today. Something that we don't perceive, we say it doesn't exist. Higher dimension, I think it is the entry to understand the deeper part of science. Without knowing the physics of higher dimension, I think we are going nowhere. So I think that the future of humanity is to explore and understand the physics beyond these limitations. Otherwise, we will stay flat. Thank you very much.